A warm welcome to the technical lecture from IIF NCTS. This is the first in the series of two lectures from Mr. Madhav Athavale on mold and core coatings. And today's subject is basics of coating surface finish, casting surface finish and coatings. A master of engineering from Indian Institute of Science, Bangalore, specializing in foundry sciences in 1980, Mr. Athavale brings with him more than 30 years of rich experience from Messrs. Foseco India Limited. During his tenure with Foseco, he gained hands-on experience in developing products for various applications in ferrous and non-ferrous foundries. He worked as a product head for coatings, cold dust substitutes, filters, and inoculants. He retired as head of technology and marketing. Mr. Athavale has presented papers at seminars of Institute of Indian Foundrymen seminars and other industry associations. He has also co-authored an educational DVD on the refractory coatings for ferrous and non-ferrous applications for NCTS, and continues to work as consultant for technical training as well as marketing. I now request him to take us through his presentation.
Today's topic, as Satish said, is surface finish of castings and sand mold and core coatings. What we will cover in this lecture is like this. We will first start from casting buyer requirements. Then we look at the importance of surface finish. Then we will look at what happens when molten metal enters the sand mold and the effect of types of alloys, types of sand and binders and their relation to surface finish, occurrence of typical surface defects, and then go into role of coating in imparting surface finish, and then also look at basics of coating, that is constituents of coating and their role. Let us first look at casting buyer needs. Now, most of the buyers of castings like this, the one which I am showing on the right hand, it's a steel wall. While specifying dimensions and properties and a particular price at which they'll buy, the buyers will specify two things. One is acceptance level for surface defects in a casting, and second, type of finish for some castings where they may specify RA or RMS values. So we are talking about texture of the surface finish, texture of the surface rather. Now, quickly a listing of surface defects in castings. One is unacceptable surface texture, that means roughness, sand fusion. Then you may have metal penetration, sand burn-on, veining, sometimes cabs or rat tails, sand drop, pinholes. Here are a few pictures of surface defects. One can see veining on the top left, metal penetration photograph at the center, casting burn-on here on the right-hand side bottom, pinholes, gas entrapment, and metal mold reaction. Then there can be some things which can come because of retained particulates. Sand plus coating particles may remain. Then erosion, which can be because the surface has weakened and has got washed away. And in HGIN castings, large HGIN castings are under certain set of conditions, you may get graphite nodule degeneration on the surface, as you can see it here. Now let's back and look at what is the importance of casting surface finish through some examples. Now, why is surface finish important for a casting buyer or a casting user? One, it can be simply an aesthetic need. The casting looks good. Or it can be a functional requirement. Let's see a few examples to just amplify what I mean by this. Now, surface roughness is a good indicator of the performance of a mechanical component. For example, say irregularities on the surface, they may become nucleation sites for cracks or corrosion, as can happen in cylinder heads. I have a photograph for you. In aluminum cylinder heads, a rough water jacket sand core surface is known to have resulted, or it has caused initiation of cracks in operation. And here is a micrograph of such a picture. On the left hand side here is the sharp corner on the surface because of roughness, from which this crack has originated, as you can see. For some applications, roughness may be desired to promote adhesion for cosmetic finish, such as painting, powder coating, or plating. As an example, look at these two. This is tabled in a enamel tableware, where after making a casting, then a coating process is being done. And roughness, uniform roughness of the cast surface is very important to get good painting on the surface of the bow. Long ago, when I had visited a foundry in Taiwan near Kaohsiung, I happened to see this particular example. That foundry, using a desaline, was producing the bowls of this type, the castings for this tableware. And they were looking very uniformly rough, but they were rough as compared to their older plant, where they had a surface finish which was a conventional jute squeeze line. And then at the bottom, it was a very fine finish. On the sides, it was a relatively rough finish, as happens in conventional jute squeeze line. And while talking with the foundry owner, he said he prefers desaline because while the surface finish is coarser as what they want, it is also uniform. That's why it is preferred. So that was an example for me. Now let's look at a turbocharger housing, a turbine efficiency. This is a stainless steel casting. And here are the studies. This is taken from a paper which studied the effect of surface roughness on the efficiency of the turbine. On the left hand side, on the graph that you see the red spot, red points, which are the actual readings from hot gas stand readings, and the triangular ones are CFD model readings. And you can see they match fairly well. But what is important to notice is, as the average relative surface roughness increases, that moving from left to right, you will find that the turbine efficiency on the y-axis, what is mentioned is not absolute efficiency, it is change in the turbine efficiency. So net, if you see, there is a drop of almost 4% in the turbine efficiency, and that means a lot. 4 different steel turbine housings with different volute roughness levels were tested. These are the 4 points which have been plotted. The volute surface geometry checked by CT scans. They are within the tolerance of plus minus 0.3 mm. And as I said, penalty in turbine efficiency due to increasing measured surface roughness was around 4%. Let's take another example. We see a wall and you see a very nice clear lettering on that, which is a buyer's requirement because you want traceability for the casting in the service. Another example, the surface roughness of hydraulic passages in a pump has a very significant impact on the Reynolds number of the fluid flow and efficiency of the pumps. And the change in efficiency can be as much as 10 to 15%. This also is available with me in the form of an excellent paper which studied this volute passages as well as the surfaces on the impeller vanes. And so in short, the prepared mold and core quality has to take care of this particular aspect because it has a direct bearing on the surface finish, on the efficiency of the component. Now, having looked at examples which tell us why, for aesthetic reasons, surface finish is good, I'm sure you would have many more examples like this. How do we go about measuring the surface roughness? The two most common are average roughness, which is a calculation of average length between all the peaks and valleys from the mean line of surface. Then another commonly used measure is root mean square roughness, which is calculated using an algorithm that finds the square root of the average of squares of the value. Basically, RMS turns the surface profile into a sine wave and measures the average deviation of the curve from a mean line. And that means apart from profilometers, one simple good visual gauge is what I have shown, which is cast microfinish comparator, which many of you would have seen. And as you can see, it gives you the RMS values. If you look little closely, you will see for different types of cast surfaces, whether it is die casting, investment casting, shell molds, etc., normal non-ferrous sand, normal ferrous sand, how the roughness goes on increasing. And here you see the roughness going from RMS value of 20 to RMS value going all the way up to 900. So this is used as a visual comparator for inspection of the castings. I'm sure many of you would know this, many of you might be using this. Now, let us look at mechanism of formation of some of these defects or formation of roughness on the casting surface. So in brief, what we are going to look at is metal mold interaction or metal core interaction, which then can result either in a defect called metal penetration or sand burn-on, sand fusion or veining, and sometimes in scabs and all other ones that we saw earlier. But what I'm interested in sharing with you is the physics and chemistry of the surface defects as well as surface roughness. Now, as we said, there are one is your sand mold. What I'm talking about now is going to be all about sand molds and cores. There are mold and core parameters, and there are molten metal parameters. And it is finally the interaction between the two which decides the casting surface quality. What are these molten metal parameters which are? One is chemistry, then its reactivity with oxygen, its reactivity with the mold and core medium or mold and core sand. The temperature, chemistry will also decide what is the melting point, as well as adding superheat, it tells you what is going to be your pouring temperature. What is the fluidity of the metal? Because chemistry also decides how fluid the metal will be. As all of you know, pure metals will have the highest fluidity, while either hypo or hyper is going to have lower fluidity because of the nature of solidification. Then what is the velocity with which the sand surface is encountering the metal as it flows in? Another factor that is important from metal side, from casting design or side, is what is the head height of the metal. We will see the physics of this in next slides. On mold and core side, again, a similar ones, chemistry of the sand. So whether it is silica sand, zircon sand, chromite, olivine, what is the shape? Is it rounded, acicular, angular, subangular? What is the distribution and average grain fineness number, GFN or AFS number, as well as size distribution or grading as we call it. Then what is the packing density as well as the permeability? Permeability is the outcome of the two things. One is the packing density, which in turn is impacted by the shape and size distribution. Then another important point is the thermal properties of the sand. So what is its fusion point? How good is the refractoriness of the molding medium? Does it expand and how does it expand? So does it distort abnormally? Then what is the behavior of the binder which is used for binding the mold and core sand? Is it organic binder? Is it silicate? Is it clay? And then thermal properties, so chemical properties as well as thermal properties of the binder system. Generate gas. Reaction. I have put here Hatfield manganese steel. So manganese reacts with silica to form manganese oxide, and then manganese oxide again reacts with silica to form liquid manganese silicate. This is what happens in case of Hatfield manganese steels. I'm taking this as an example. We will see one more when we go into the physics and chemistry. I'm not going through the lower stages, because this liquid manganese silicate, there can be a range depending on the chemistry. Now, the types of sands which are typically used for molds and cores. Most common one is silica. Then relatively less common, but still these days more and more used for manganese is olivine, then chromite and zircon. Zircon, of course, is common for steel castings. Chromite is used for specialized uses, can be used for both steel and manganese steel castings. Another thing that we should remember is both olivine and chromite, they are sort of manufactured sand. They are crushed from the stones, or sometimes you may find deposits. Silica also, naturally occurring silica sand, or one may use, especially in steel foundries, I have sometimes seen people using crushed quartz, which is purest form of silica. I'm not going to go through rest of the properties. All that I am saying is as you move from silica to olivine to chromite to zircon, the density keeps on increasing. Specific gravity increases. Bulk density also increases. Very importantly, sinter point also increases. From 1730 of silica to around 1860 for olivine to about 2000 for chromite and about 2200 for zircon. As regards thermal expansion, silica, because of the crystallographic transformation that it takes place from quartz to tridymite to crystallite, so it expands highest, while olivine is relatively less, chromite lesser than that, and zircon has the least. Metal mold reaction is high with silica, as we have seen in case of manganese steel, even with iron oxide. Polymer has lower reaction. Chromite has lower reaction. Go except in manganese steels. And for manganese steel, it is for the simple reason that there is silica present. When zircon is ZrSiO4 as a chemistry equation, but it is actually ZrO2 SiO2. And utilization, as all of you are aware, silica is commonly used for almost all metals, but then you need to use proper measures like coatings to ensure that you get desired surface finish. Here is a quick look at expansion of sands. As you can see, silica shows very sharp expansion around 573, 575 degrees as the phase change happens. Then there is olivine, chromite, and zircon, which have lesser and lesser amount of expansion associated with them. Now, if there is too dense a packing, there are two parts. One is what is the inherent expansion of the sand, as is seen in this graph. The other one is there too dense a packing of the mold and core, because that can create stresses and result in surface defects, such as surface spalling and then causing rat tails or scabs in hotspot areas. In extreme cases, cracking of the surface leading to veining. We'll look at the mechanism of veining later on. Here are pictures of two sands and effect on compaction. On the left-hand side, I have taken picture of typically, Allahabad sand, which is quite popular in northern part of the country, subangular to angular. While I have taken a photograph of a typical German sand, which is subangular to rounded. So what is their effect on packing density? As we said, packing density depends on grain shape and grain size distribution. Good packing or good compaction of sand mass means lower surface roughness. So smoother mold or core surface. And it also means that the pores which are present on a compacted mold surface, uncoated, the average diameter of the intergranular pores will be smaller. Subangular to rounded shape gives optimal combination of compaction and permeability. Now, having looked at the nature of sand and the packing, let's have a quick look at binder type and casting defect tendency. Here I have taken 4 organic binder systems: acid set phenolics, acid set furan, ester set phenolic, which are alkaline phenolics, polyurethane no bakes, and our good old alkyd no bake. Only from surface finish point of view, tendency for surface defect, if you see, veining, ester set phenolic is not prone, very little prone for veining. This is taken for silica sand, mind you. Scabs and inclusions, only in alkyd no bake the tendency is more, as well as in polyurethane no bakes. Hot tearing tendency, most of them are less prone or not prone. Lustrous carbon defect, polyurethane no bake will be very prone, while it is rest of them are not so prone. Nitrogen pinholing tendency, we had looked at pinholes as one of the problems. Here, acid set furan resins or polyurethane no bakes or alkyd no bakes, they are prone for nitrogen pinholing because of the chemistry of the binder system. One important omission here really is sodium silicate CO2 system. And sodium silicate CO2 system, in terms of veining and scab, it would have much less tendency for formation of these defects, but it will have higher hot tearing tendency because of its poor collapsibility. Lustrous carbon effect question will not arise there, and nitrogen pinholing tendencies also will be less with sodium silicate binder system. Now let us look at physics and chemistry of surface defects. I'm going to cover metal penetration, different levels, sand fusion. Now, pressure due penetration of a molding aggregate is the title of this slide. What I want you to look at is, here is a schematic. On the left side, what you see, rows of sand grains, which forms a mold or core surface, and there is liquid metal. And through the pores in the sand grain, we see some metal gone in. Now, H is the head height. LP stands for length of penetration inside the mold or core surface. Now, whether metal penetration will happen or not is really a function between the pressure balance between the different types of forces which are acting. The ones which are pressing down are PST, P dynamic, that is pressure, static pressure, dynamic pressure, and expansion pressure. And the ones which are resisting these pressures are the capillary forces. Then you have frictional forces and back pressure coming from any gases which are coming out of your binder system. Let's look at little more details. Now, P static is simply a rho into GH. Rho is the density of the metal, G is gravitational force, and H, you know, is the head height. P dynamic, because this sort of represents the dynamic pressure, the kinetic energy which the metal gets because of the speed with which the metal is entering. So the way your running system has been designed, what is the geometry of the casting? Geometry of the casting has a big impact on PST, while P dynamic is being decided by not only geometry of the casting, but design of your gating system as well, which is equal to rho into V square. V square is the velocity of the metal facing the mold or core, mold and whatever pressure is coming on the mold or core surface. So rho V square by 2, which is dynamic pressure, and pressure of expansion. If you take steel castings, it is nil, but if it is iron casting, then there will be some expansion pressure because of precipitation of graphite. This will be especially true both in case of very large iron castings as well as gray and HG iron castings being cast in green sand molds. Now, PF stands for frictional forces, and the equation is mu by K into LP into Vp, where mu is the viscosity of the liquid metal, K is the permeability of the molding sand, the length through which the liquid flows. In this case, it is the depth of penetration as seen in the picture there. And Vp is the speed with which the metal moves through during the penetration. Then we have P gamma, which is capillary forces, where gamma LV stands for the extension or liquid metal vapor surface energy. Theta is the part between sand and the metal, and dE, the term in denominator, which is the average pore diameter between the sand grains. And mind you, direction, the resisting forces are in upward direction. We have put a negative in this equation against this formula. P gas can be between 1 to 1.25 atmospheres as well as has been measured in the experiments. Now, there are two ways of penetration and metal mold reaction can happen. The penetration inside the mold surface will happen when the static pressure plus dynamic pressure exceeds the resisting forces of frictional force and capillary forces and gas pressures. So mechanical penetration in castings, it can happen in all ferrous castings. And as we said, the variables are a metallostatic head, metal velocity, and grain size of the molding aggregate and the way the surface has been compacted. The grain shape and size have been found to have a major influence on the surface roughness. So what do we do in this? Can be taken to eliminate mechanical penetration with one application of a mold coating. Because of mold coating, we are introducing the fillers into the pores in the mold or core surface, thereby reducing the diameter of the pores and thereby increasing the resistance to metal penetration. Plus, by applying a layer of the coating on the surface, of course, we are making it more impervious. We are decreasing the flow rate of the into the mold so that the pressure will be less. And important thing is choosing such a molding aggregate, the type of sand, the type of binder system, which is less susceptible to wetting. That the metal mold reaction tendency, as we saw in case of manganese steel earlier, can be less. Now let's have a quick look at chemical penetration, and here is a photograph on the left hand side. This is for steel. In case of steel, the reaction that happens is that iron gets oxidized in presence of oxygen in the mold. So twice FeO plus SiO2 coming from the molding medium, it forms Fe2SiO4, which is phthalate, and that wets the sand and that produces the chemical penetration. Saw was mechanical, physical penetration, and now this is the chemical penetration. In our day-to-day experiences, both for iron and steel, we will find a combination of these. There can be simple mechanical penetration, or there can be mechanical penetration which is further exacerbated by the chemical reaction between the metal and the molding sand. So, no, the things which are termed as sand burn-on, sand burn-in, they come into the picture. I have not used those terms here because that was the classical way of defining the metal mold reaction. The experiments, at least in the laboratories, suggested that the chemical metal penetration is predominant in steel castings, even though it can happen in some of the iron castings. But what was found, at least under laboratory conditions, was that only when there is an oxidizing mold atmosphere, then there is a likelihood of chemical penetration. True in case of steel. High carbon steels are less prone. This has been found. High carbon steels are less prone for penetration as compared to low carbon steel because excess carbon protects the metal from oxidizing. Same is true for cast iron. Manganese steel, of course, is prone for chemical penetration because MnO2 readily reacts with silica sand in the earlier equations. So use of appropriate coating fillers like magnesite, use of different base sands has to be used to prevent metal penetration in manganese steel casting. Now we go to next kind of defect, which is sand fusion. And here is a picture of that. The fusion occurs when sand grains fuse with molten metal. This appears as a thin crust with a brittle, glassy appearance, which is firmly adhering to the casting surface. It is found that if the molding or core sand has poor refractoriness due to low melting phases in the present in the sand with minor elements like iron oxide and silica sand, then this can be a problem. Sometimes in clay bonded sand, fusion can happen if the clay refractoriness, because clay has low refractoriness and it also has iron oxide. So if one doesn't, especially in green sand molding, if you doesn't take care of the dead clay that is built up into the sand system in green sand molding, then you can land similar problems. Another thing that sand fusion, of course, is higher than normal metal pouring temperatures. We saw the mold side, which is sand and anything else like clay going there. The other side is you pour the metal at abnormally higher temperatures than what is the, and then you will get the sand fusion. Now, after fusion, let's look at veining. And here is a schematic for that. See, when the liquid metal comes in contact with the mold or core surface, initially the first layer that we see here, that will expand. But as it crosses 575, it softens and starts shrinking. While the layers which are around 575 degrees, they are expanding because of the crystallographic changes which are happening in silica sand. This I am explaining for silica sand. While the layers below are still below 575 degrees, that is below the transformation temperature. So what is it that happens? Because above 573 degrees, there is a softening of the sand and they start shrinking. So while on the bottom side, there is a linear expansion. So there is expansion happening on the top. There is expansion happening at the bottom. Contracting sand on the surface and expanding sand directly beneath the surface creates tensile failure, and that will cause a crack in the surface and liquid metal gets into it. As you can see, here are a few pictures of veining happening. You can see a section of what looks like a hub. So what are the factors that influence the veining? It is grain size and grain particle distribution. Then intensity of compaction, higher the intensity, it increases the stresses. The base material, is it silica or what is the expansion nature, thermal conductivity of the molding medium? And what is the nature of molding material, binders and additives? Do they decrease the stresses or the suppression of silica expansion due to thermoplasticity? So this also has an effect. What you see at the bottom, I think, is perhaps a section of ventilated brake disc, as you can see. And of course, the casting temperature, role of that we saw earlier. Now, after having looked at the various levels of metal penetration, which is mechanical penetration and chemical penetration and combination of them, as well as veining, and we also had a brief look at the because of the binder. I have not covered scabbing here. Scabbing is much more predominant when there is green sand. Let us look at Now, the role of coating in imparting the surface finish. Coating is one of the most used for getting the desired surface finish for the casting. And I would say the governing equation for that is P gamma is equal to twice gamma LV by dE cos theta. Capillary forces, smaller the dE value, that means finer your sand, better the compaction, the resisting pressure is going to be higher. What coating does is it fills these pores and reduces dE. By having proper chemistry, it will also take care of wetting, which is cos theta, while gamma LV is much more a function of the metal which is being the type of sand or type of refractive in case of surface finish, in case of coating, will also have an impact. That is the way it is going to act in deciding the surface roughness or presence or absence of surface defects. Here is a presentation of how, of a very simplistic, almost basic level. Here on the left hand side, you have a mold aggregate, a surface and metal in contact with that. And this is how, after knockout, you will have a surface of this roughness. While on a coated mold, because of all the physical cavities and are filled by a coating layer, you will get much more smoother surface finish on the casting. Now let's look at what are the constituents of coating. Let's first define what are the characteristics of good coating. One, it should minimize the core strength degradation, because the constituents of the coating can attack the binder system and weaken the core. So the design of coating has to be such that it doesn't degrade. It should provide adequate protection against metal penetration by way of proper selection of constituents. It should have good stability on storage, covering power, that has to do with the consumption. The good application properties by whatever method that you are choosing. And we have a very brief look at them. The coating should level well, and it should have minimum to get a smoother finish. Otherwise, you will get undulating finish. Refractory properties cope with the metal that is being poured. Good adhesion to the mold or core surface. It should not spall, it should not get washed away. It also should have certain level of permeability to minimize air entrapment. It should be fast enough in drying. It should not have any tendency of blistering, cracking, or scaling on drying, because that will disturb the mold and core surface and will cause defects in the casting surface. Obviously, it should have good suspension and good remixing properties in order to ensure that during application, you don't get homogeneous application consistency. Now let's look at what are the basic components of a coating. One of the most important functional part is your refractory filler. Then comes the binder, which helps bind the refractory filler to the mold and core surface. Then you need certain suspension agents so that the refractory filler remains well suspended in the carrier which is used in the coating, which is here. And you would need certain additives to give one. It should avoid any degradation of the coating in storage. Help decide the flow characteristics of the coating, which is called a rheology of the coating, and wettability of the coating with the substrate. That is what the additives do. So again, refractory fillers, binding agents, suspension agents, liquid carrier, and then you have your additives. This is what comes from coating and goes on to the substrate, which is your mold or core surface. Now, what type of fillers are commonly used? Can be graphite, it can be silica, it can be zircon, magnesite, various types of aluminosilicates, magnesium silicates, which is talc. In carriers, most common and most preferred because of environmental reasons is water, different types of alcohols, or in some special cases, there could be some other organic solvents. Binders can be modified starches, clay, sulfite lye, resins, both natural and synthetic. In some cases, sodium silicate, especially in die coatings, which we are not covering right now. And for high temperature bond aluminum orthophosphate, this is a specialized binder. It gives you high temperature bonding for the coating onto the surface of the mold or core. And then come the additives, which are defoamers, surfactants, preservative, viscosity. So these are the constituents of coating. Let us have a quick look at what these are. Let's look at what is the ASTM definition of refractory. That definition says the capability of maintaining the desired degree of chemical and physical identity at high and in the environment and the conditions of use. This is how ASTM defines a refractory. So both chemistry, physics, which is the right for high temperature use and any other environmental conditions. Pictures of minerals which get used as fillers. Silica is quite common, especially for iron castings. Zircon, as we saw earlier, zircon, we saw it in terms of sand. Now I'm talking it used as a filler. Then pyrophyllite, mica, these are all varieties of aluminosilicates. Then natural graphite or plumbago, which is another very popular filler for especially for iron casting. Deadwood magnesite for manganese steel, but there dead burnt, that is the most important thing, plus MgO content, because usually magnesite will have a as well. So it is essential that magnesite has high level of MgO, like 90%. Sillimanite, which is again aluminosilicate. This is another one which is commonly used in India. As you can see, all of them have center points which are pretty good. Zircon greater than 2200, pyrophyllates around 1600, depending on the chemistry really. Agro has very high center point. Magnesite has got very high center point. And sillimanite also has a decent center point. With the application of the refractive mold and cores that comes in contact with molten metal, The refractory particles tend to fill the pores on drying. I'm repeating this. These are the fillers. The typical gradings which are used for fillers are usually between 200 to 300 mesh. Very quickly, important filler characteristics. Suitable particle shape, what is called as aspect ratio, which is average diameter to average thickness ratio. Higher aspect ratio gives higher reinforcing effect on the coating matrix. This is about coating as supplied. Particle size, as I said, 200 to 300 mesh. Chemically inert to molten metal, so it is not readily wetted. Should not contain volatile elements that produce gas on heating. Consistent cleanliness and pH. This is especially true for those which are processed, like you may have chromite or you can have magnesite, which will carry some gangue minerals. pH indicates whether it is acidic or basic and the reactivity with the metal. It has to be compatible with, see, we discussed about any currently used normal chemical, common chemical binders, but this is slightly futuristic. Whatever you choose has to be compatible with any new binder system may come. Let's have a quick look at carriers. Now, liquid carriers is a medium which contains the coating constituents. It also serves as a vehicle to transport the filler material onto the sand substrate, which is straightforward. It can constitute about 20 to 40% of the coating depending on the formulation that we are using. It has to be dried and removed to prevent gas formation when the hot metal is poured in the mold, because formation of gases may cause casting defects. It also must be compatible with sand binder or refractory. It also must be compatible with method of drying or its flammability or burning characteristics, toxicity and odor, how much labor is required, what is the floor space that is available, etc. Carriers are water, aqueous carriers, and spirit-based carriers which will contain organic solvents. Let's look at water. This is the safest carrier from environmental point of view, but it requires heat to dry the water-based coatings. Complete drying of deep pockets in a reasonable time can be a difficulty. It also has a greater tendency for tears or runs compared to organic based coating, simply because it doesn't dry fast enough. Runs means the excessive flow of the filler material. Tears means it is not adhering fully. Tear drops are forming. It reduces the tensile strength of, say, PU novae cores. It increases the potential for core breakage. It also causes degradation of the core properties in storage. Not so much in some parts of India, as well as many parts of the world, water-based coatings can freely cold climate, so you need to have proper storage. Or solvent-based carriers or spirit-based coatings usually contain isopropanol or methanol or ethanol as liquid carriers, and these are dried by igniting and burning off the alcohol, in this case isopropanol. Isopropanol is large molds and cores, since that has got good combustion characteristics with slow burning front and a moderately hot flame, because burning alcohol also can be a problem when we are looking at large molds and cores. Chance of overheating the sand surface and so sand friability, or fast burning alcohols, lower alcohols like methanol, ethanol, they may burn or they evaporate, and on the large surface, if you are not coating it by parts, then you can have problems of poor bonding properties, because the heat that is coming out of the carrier also helps the formation of bond because of the type of binders which are used. Also technically acceptable because it is acceptable with wide range of suspension agents and resin binders. So solvent has to take care of everything. Organic solvent based. Sometimes air carriers such as carbon tetrachloride, methylene chloride, chloroethane, chloroform, in special applications where you don't want to flame out the coating, you want it to evaporate in air itself, but then they are hazardous. Also, their chemical nature is such that they are not as versatile as isopropanol in the formulation of foundry coatings. In many cases, specialized form of gelling media as well. We are considering all the aspects. The organic solvent-based coatings are discouraged because of the environmental issues. Now let's look at carrier liquids, a quick overview, most commonly used. Water, chemical formula H2, methanol H3OH, ethanol C2H5OH, and IPA will be CH3 twice CHOH. They have water at the highest boiling point, and then from methanol to IPA, the boiling point increases. Density of most of the alcohol, they remain around 0.8. Water is 1. Flash point of IPA is relatively higher compared to ethanol and methanol. Evaporation index also. What we mean by evaporating index is it is a ratio of liquid evaporation time with respect to dye as a standard liquid at 20 degrees. That is the way evaporation index is checked. On the left hand side is ethanol. Ethanol will tend to give you a slightly bluish flame, while IPA will have a yellowish flame and it will be slightly soupy. Let's have a quick look at suspension agents. Bentonite based clays for water carrier, because bentonite swells and forms gel when mixed with water, but you have to allow certain time for gelling to happen properly. As those of you are familiar with even bean sand molding, you know we check gel index of bentonites. They also control the flow properties of the coating, and these flow properties are designed to suit the application method that is used. Suspension agents can make up from 1 to 5% of the coating. Somebody may ask why such a wide range. It depends on what kind of a filler you are using. If you have a lighter filler, you may require less amount of suspension agent. Higher the suspension agent, the tendency for shrinkage cracks when it is dried can happen. Now, bentonites were very common in the earlier days, but now substitutes are used in polysaccharides, certain carboxymethyl cellulose. Then is what, but polysaccharides they require special. So it requires special mixers in the sense the blade design and the RPM are very important. Rotational speeds. Modified bentonite known as organic bentonites or bentones, they gel in the organic liquids such as coals and solvents. Bentones result from base exchange of inorganic calcium and sodium cation for an organic one, ammonia. Now, examples of suitable suspension agents for organic solvent carriers are hydrogenated castor oil and quaternary alkyl ammonium montmorillonite gel, which is the technical name. We call it as bentones. Organo-modified clays is another terminology that is used. Now, binders. Binding agents are various materials which act to hold the particles of the refractories together and attach them to the sand surface. The quantity of the binder increases as the particle size of the refractory decreases, thereby increasing the surface area for a given ratio in a coating. So, supposing your filler is say 50%, but the size and sieve distribution is different, then finer the particles, more is the amount of binder required because surface area of the filler is high. As a matter of principle, one should use the minimum amount of binding agent which is required, but there has to be an optimum level. Too less a binder and you will find that the adhesion is poor and the filler will get washed off as the metal enters. If there is too much of binder, then the coating surface may be brittle, may crack, may give. It may also lead to higher gas levels because resins and organic binders, they evolve gas. So any undispersed binders in partially dried area, molds and core will cause gas defects. Now, another important point for binders for water-based is most of these organic binders and many suspension agents, they are subject to biological degradation. So, longer storage of coatings, precautions have to be taken to suppress these reactions. So, usually the coating producers, they will add biocides to prevent the bacteria formation and fermentation. In spirit-based coatings, that doesn't happen. And the binders used in water suspensions are sulfite lye, various types of clays, dextrine, molasses, sugars, phenol-based resins, which are soluble or miscible with water. In spirit-based suspensions, natural or synthetic resins, which include furan, phenol, formaldehyde, PN, novolax, and natural wood resins are pretty common binders for solvents. Quick look at specialty additives. And here I'll show a video. You can see on the left-hand side, the coating is glass at all because there is not enough wetting agent in it. While on the right-hand side, you will find coating adhering onto the surface of glasses. Same can be done even on glasses or shapes made out of glass. There are different tests which the coating developers and manufacturers use. This is one of the common ones to show the effect of wetting agents. Let's have a quick look at rheological behavior. That is viscosity versus shear force or shear rate actually. When we take plain simple water, which is called as Newtonian fluid, because there is no change in the viscosity, when a shear force is applied. So when there is a shear applied, there is no change in viscosity. When there is no shear, still there is no change in the viscosity. I mean, imagine taking a bath of water and putting a core inside it. You'll find that there is no change in the viscosity of the water. Now, here, coatings, we want the coating to remain onto the surface of the mold or core. So, let's look at what we call as thixotropic fluid. What I would like you to imagine is, imagine that you have got a coating which has got a thixotropic behavior. What we mean by thixotropic, that when you apply a constant shear here, applied. So imagine you are dipping a brush into the coating pot, taking it, and then as soon as you dip it inside, the viscosity drops slowly, relatively slowly. It doesn't drop suddenly. And the coating comes onto the surface of the brush. Now, once you start applying the coating onto the surface, see, as you brush out of the coating, there is no shear being faced by the coating, so it freezes. And when you are applying it by applying a force onto the surface of the mold or core, then again the viscosity drops, the coating spreads onto the surface, and when you are stopped, because there is a slight delay in regaining of the viscosity, it allows leveling of the coating to take place. This is called as thixotropic fluid. So we need this kind of thixotropic behavior for coatings which are brushed or swabbed. They allow the application of highly filled coatings, that means filler levels are high, onto the surface, and at the same time give you relatively better surface finish because it levels off. Let's look at the other extreme. A special case of thixotropic fluid is pseudoplastic fluid. In this case, there is a very sharp drop in the viscosity when you apply the shear, and it remains low. And as soon as the shear force or shear force is stopped, shear rate is stopped, then the viscosity comes back to the original level very quickly. So I'm showing it as sharp drop, remaining low at low level, and going up very sharply. So this is the kind of viscosity behavior that is required for our dip washes. Imagine the core being taken and dipped into a bath or a tank of a coating. As soon as the core enters the liquid coating, its viscosity drops and it spreads and covers your coating, all the nooks and corners of your complex core, maybe ventilated brake disc, maybe a water jacket. And as soon as you have taken the core out of the coating bath, it freezes in place. So it stays onto the surface. So this is what is required for a pseudoplastic, required for a dip coating. When it comes to, before I go and continuing the importance of rheology, improper rheological design of a coating will mean poor coating coverage, uneven coating thickness, coating blisters, rough surface. Coating should effectively wet the substrate and should key in into the surface. That will then prevent slumping or sagging of the coating film, or flow marks or bead formation will not happen. So in summary, surface finish is a very important requirement of casting, either from functional or aesthetic point of view. Metal factors and mold and core factors impact the metal mold interaction, mechanical as well as chemical, and thus roughness of the casting surface as well as presence or absence of surface defects. Mold and core coatings play a key role in achieving the desired surface finish by providing mechanical and chemical means to negate the adverse effects and enhance the positive effects of the metal mold interaction. Coating formulations need to be designed very carefully to achieve the good casting finish by having the right proportion of right type of constituents to get a balanced performance for a given type of a casting as well as given type of mold and core that is being used. This, in summary, is what we have covered in today's lecture.